Section 14.7, Bernoulli's equation. So if we imagine having a tube with an ideal fluid flowing through it, because we're only going to assume ideal fluids for this chapter, and so we have an input on one side where there's some pressure acting on the fluid on the input, the fluid is moving at some velocity, it's held at some height, and we can compare with a later instant, right? So after some time has passed, the fluid is now further along in the tube at a different height, y2, moving at a different speed, v2, and there's a different pressure acting on it from beyond on the output side there. So if we apply the conservation of energy, one of our key big equations that keeps popping up, for equal volumes of input and output fluid, we could derive this equation. And there's details in the book on this derivation. I'm also happy to talk about them through with you in office hours or through an email. So you're welcome to reach out to me on that. But here it is in short, that the pressure at one point plus 1/2 the density times the speed squared plus the density times g, our 9.8, times the y, the vertical distance or the height. Those quantities on the input side must be equal to those same quantities on the output side. The 1/2 rho speed squared is called the fluid's kinetic energy density. It's almost like kinetic energy. We know kinetic energy is 1/2 mv squared, but now it's mass per unit volume or density. So that's why we talk about it being the kinetic energy density. And you can think of the rho gy as the potential energy density, because it's much like our mgh. We're just working in terms of the density here. Now, one key distinction is the P by itself is not density. This is pressure. It looks a lot like the density variable of rho, but this is a P for pressure. So we can't just divide out the densities unless the pressures disappear first. Right, so this is Bernoulli's equation, the conservation of energy in fluid form. It's a really great equation. Another way that we could write it, since it is a conservation equation, is that all of the quantities at one instant in time, the pressure plus the kinetic energy density plus the potential energy density, have to remain a constant. They have one set summation, and you can look anywhere within the fluid's flow, and that those values will always have a constant summation. So these are two different ways to write Bernoulli's equation. And they tell you about a fluid that is moving, that can have different heights and different pressures. Now we can check, what if we make our fluid at rest? Well, if we set our velocity is equal to 0, then we find we have a static fluid, which matches our equation that we previously got, equation 14.7, for a static fluid, where you get more pressure as you go to greater and greater depths. But Bernoulli's equation now can account for if the fluid is also moving. That can be another factor that changes the pressure. Similarly, we could say, well, what if we have a horizontal pipe where the fluid is always at a constant height? Well, in that case, we could set that y1 is equal to y2, and so our potential energy density terms would cancel out, and we would get this expression, that the pressure plus the kinetic energy density at one instant must equal the pressure and kinetic energy density at another instant in time. This is really useful for analyzing how the speed influences the pressure. So if for some reason the speed, like v2, is greater than v1, well, we know that we need to get to that constant value. So if the speed goes up, that tells us the pressure must go down, where this is my pressure P, not a rho, and this is my speed going up. Similarly, if the speed of the fluid decreases, if it starts traveling more slowly, then there's going to be a greater amount of pressure. This sometimes seems a little bit counterintuitive to what we're used to. If we think of something traveling fast, we don't think of that as being low pressure. But be very careful looking at the equations, and you can keep it straight. And we'll see some examples of this in a little bit. But first, let's take a look at a checkpoint. So it says water flows smoothly through the pipe shown in the figure, descending in the process. Rank the 4 numbered sections of the pipe according to A, the volume flow rate RV through them, B, the flow speed V through them, and C, the water pressure P within them, greatest first. This is a really key example, and there are a number of different ways to think about it. So I really want you to take some time and get an answer to parts A, B, and C before you watch the rest of this video. So please go ahead and hit pause now. Okay, I'm gonna trust that you did that. This is really hard for me to do. So one of the hardest things with this example is it's hard to know what changes and what stays the same, and what changes influence the others, right? So do we figure out the pressure and how that influences the velocity, or the velocity, how that influences the volume flow rate? How are these variables connected? Well, this problem in particular gives us a clue in the order in which it asks the question. So that's something you can pay attention to. Problems don't always do this. They don't always guide you through the process, but this helps to teach you the process so that when you have less guides, you're more confident in how to solve it. So notice it first asks for the volume flow rate, RV, through the pipes. The volume flow rate we saw in the last section, the continuity equation, the volume flow rate must be constant, assuming it's smooth flowing ideal fluid, which there's nothing that indicates this is not. So that tells us the volume flow rate must be the same for all 4 segments of the pipe, right? And we know the volume flow rate you can calculate with the cross-sectional area times the velocity. So those 2 things at one instant must be equal to the cross-sectional area times the velocity at some other instant. This also then guides us to part B, because part B says the flow speed through them. And notice this equation just depends on the cross-sectional area and the speed. We've already set that this equation is true, so this is the fastest way to get our velocity. So we can note that if the cross-sectional area increases, it's going to be a lower velocity. If the cross-sectional area is smaller, it's going to then be a larger velocity. So notice 1 is the smallest area, so it's going to be the biggest speed, right? 2 and 3 have equal cross-sectional areas. So those are going to be equal speeds. The area hasn't changed, so the speed hasn't changed either. And then section 4 has the biggest cross-sectional area. We imagine drawing that in there. And so it's going to have the very smallest velocity. All right, and it says to rank them greatest first. So we are in good shape for our 1, 2 equals 3, and 4. And by following this procedure of figuring out that the volume flow rate's constant, that determines the velocity, it makes C much more straightforward, because C is looking at the pressure within them greatest first. And we know that pressure is going to depend on both how fast it's going and how high it is. So that gets us back to Bernoulli's equation that says that the pressure at one point plus our kinetic energy density, 1/2 density times V squared, plus our potential energy density, rho Gy, that these have to be equal to a constant. All right, so we're trying to figure out the pressure, and so we know it's going to counteract whatever happens with the velocity and with the y. So notice with case 1, that is at the highest height and is moving the fastest. So in other words, the velocity is up and the height is up. That means our pressure needs to be super low up there. 2, the velocity isn't quite as fast, so the pressure can be a little bit larger. 3 is the same speed as 2, but now it's lower. So for case 3, we're seeing that the y is now smaller, so we could call even the y 0 if we wanted to. We could set this down here as y is equal to 0. So we see that our velocity has gone down, but really our y has gone down. Right, if we're looking at these terms. So these are both down compared to 1, and so our pressure is going to be up. And similarly, 4 is at the same height as 3, but it's moving even slower. So for 4, our velocity is way down, and so our pressure can be extra up. So that we see the exact opposite of the velocities and the heights with the pressure. So if you have more height and more velocity, it's going to be less pressure. If you have less height and less velocity, you can then have more pressure. So let's check how we did with this. All right, so we see they do have all the same volume flow rate. 1 is moving the fastest, then 2 and 3 to high for the same speed, and 4 is the slowest. In terms of pressure, 4 has the highest pressure, then 3, then 2, then 1 has the lowest amount of pressure for the reasons we outlined before. If you have questions on this, please do reach out to me. I would love to chat further on this. I know it's not the same as getting to discuss it in class, so please do keep the discussion going. All right, I wanted to highlight a couple of examples of Bernoulli's equation because it is all around us. So one is a glider. The lift force comes from Bernoulli's equation. And that's because with gliders, the wing is a little different than you might think. The bottom of it is smooth, and then the top, it bends upward, bows upward. What does that mean? Well, the air below can travel in a direct line, but above, it needs to bend around the wing. So it has to travel further, but it wants to meet up with the air again. So it's going to travel faster to meet up with the same air. So if the air above is traveling faster at a higher speed than the air below, that means faster air, lower pressure. We're creating a pressure difference where there's lower pressure above and higher pressure below. If there's a difference in pressure, that means there's going to be a force. So the force will go away from the higher pressure towards the lower pressure. It's an upward force known as the lift force, which is why an airplane can glide through the air. Pretty nifty. Another example is the P-trap in a sink. So there's a water-filled trap in a sink that keeps a little barrier between your sink that's in, say, your kitchen and the tube that goes to the sewer, right? So the water here is actually a really good thing. Keeps all the stink from coming back up and emerging into your kitchen. But there's also a very particular design of including a vent to the outside. And this vent here is not just to sort of be able to air out the sewage smell. That's not really the goal. The key here is when the clothes washer dumps a bunch of water and sends it to the sewer, we now have a high velocity of fluid. If this is a high velocity, guess what that does to the air pressure right above the tube here? Well, higher velocity means the pressure is going to go down. So all of a sudden we've created a lower pressure region on the right side of this tube, and the water in the trap is going to want to join in with the water going to the sewer. It says, hey, lower pressure, that's where I want to be. So we would lose the water in here, and we would then get to smell the sewer. Now we can overcome that by just adding this vent, because then when we get a lower pressure here above, and so it ends up working out just fine, and we keep the water in the trap and we do not smell the sewer. There's much rejoicing. All right, one last example is from the great sport of baseball, which hopefully we can see again someday soon. The curveball. How does a curveball work? Well, it turns out to also be Bernoulli's equation once again. So if you throw a baseball straight without spin, then the air is going to bend around it. So here, instead of showing the baseball moving, we're imagining that the air itself is just moving around the ball. It's a little easier to depict that way. So the streamlines bend around the ball, and they bend an equal amount on either side. So they do travel faster on each side, but it's balanced out. Now, if you throw a curveball, the ball itself is spinning as it passes through the air. That means part of it is spinning against the air that's going by it, and the other side of it is spinning with the air. So the air on the side that's going with is now moving faster and is at a lower pressure. The side that the ball is moving against the airflow, the air is now slightly slower, it's a higher pressure, so it creates a deflection force towards the lower pressure so that the ball can start going in a straight line and then all of a sudden deflect towards the lower pressure. So there's Bernoulli's equation in some really cool examples. There are lots more around you, so please keep your eyes open. Look for where you can see Bernoulli's equation in effect, in application, and let me know about it, because I would love to hear more examples